Welcome back to the Deep Dive, where we wrestle complex technical subjects, grab a stack of sources you've provided, and distill those insights into pure, usable knowledge. Today, we are diving deep into a paradox that frustrates, well, nearly every computer user, I think, whether you're a casual browser, a developer, or a high-end content creator. It's the paradox of the fast computer that feels slow.
It really is. It's the single most common frustration point in modern computing.
Yeah.
You invest in a brand new, powerful CPU, you might have the latest graphics card, plenty of storage, and yet you still hit these sudden moments of hesitation or stuttering or just painful load times.
And people immediately jump to the conclusion that their processor isn't strong enough. But your source material, and you and I have gone through it, makes it abundantly clear that the real bottleneck often lies somewhere else entirely.
Exactly. Somewhere else.
So this deep dive isn't just about definitions. It's about providing you with a kind of an accurate diagnostic tool. Our mission today is to understand why raw processing speed is only half the performance story, and how the computer's architecture, specifically its memory hierarchy, is designed to cope with physical limitations.
Right. And once we understand this hierarchy, we can accurately diagnose those performance bottlenecks without resorting to expensive guesswork.
Okay, let's unpack this.
Well, we have to start by recalibrating our whole definition of computer speed. The core misunderstanding is precisely what you just mentioned. People assume speed is defined solely by how fast the chip can execute a calculation.
The gigahertz number.
The gigahertz number, exactly. But in reality, speed is fundamentally determined by how fast that chip, the CPU, can get the data it needs to calculate in the first place. That gap, that difference between the CPU's ability to calculate and the data delivery system's ability to keep up, that is the central conflict. It is truly the bottleneck of speed.
I found the foundational analogy in your sources to be immediately clarifying on this. It really moves this abstract concept of data movement into a relatable image. We're going to visualize the CPU as a highly skilled, lightning-fast chef, and the data it needs as the ingredients.
It's a perfect metaphor.
Mm-hmm.
The chef, who is capable of chopping and searing at the speed of light, can only maintain that pace if the ingredients are right there, at hand. If the chef has the salt, the pepper, the main vegetable right there on the countertop, the cooking process is instant.
But if they have to stop.
But if the chef has to stop what they are doing, walk across the kitchen, down 2 flights of stairs to a basement freezer, and then return, well, that entire process is governed not by the chef's speed, but by the walking time. The CPU is constantly being held back by its need to wait for ingredients.
That immediately introduces the necessity of this incredibly complex memory hierarchy. So why build this complicated multi-layered system in the first place? Why can't we just have one massive, blindingly fast place to put all the data?
And this is where we run into the foundational physical and economic constraints of computer science. It's the fundamental trade-off that determines everything about system design. And the source material identifies it clearly.
Yeah.
We cannot build a single type of memory that is simultaneously very fast, very large, and very cheap.
You get to pick two.
You get 2 of those attributes.
Yeah.
But achieving all 3 is, well, it's physically and economically impossible with current technologies.
So if we demand something to be ultra fast, we have to accept that it will be small and extremely expensive. And if we want something huge and cheap, like a massive storage drive, we just have to accept that it will be comparatively slow.
Absolutely. This foundational trade-off forces the multi-layered design we call the memory hierarchy. The computer uses a cascade of storage layers, moving from the tiny, ultra-fast, and costly layers right next to the chef, all the way down to the huge, slower, and massively cheaper libraries. This layered approach is an optimization, an attempt to manage this impossible trade-off by keeping the ingredients the chef needs right now as close as possible.
And understanding the relationship between these layers is the entire key to understanding performance analysis.
The entire key.
Okay, so let's start right at the top. The most prized real estate in the computer architecture. Layer 1. This is the inner circle of speed. We're talking about cache.
Cache is truly the VIP section of memory. And you could argue it's the most critical component for maintaining the illusion of a perpetually fast computer. It is a small pool of extremely high-speed memory, physically situated either directly on the CPU die or immediately adjacent to it. It is strictly designed for the absolute fastest access possible.
And its primary function is elegant in its simplicity, right? It just stores the most recently used data and instructions.
That's it. The data the CPU thinks it's going to need next, the instructions for the current operation, or the piece of data it just processed it might need again. The goal always is sub-nanosecond access time.
That immediacy is what defines it.
Yes, and what's fascinating here is the fact that even this fastest layer is itself segmented. It's a hierarchy within a hierarchy, a micro-hierarchy designed to optimize that impossible trade-off even further. Your sources break down the structure on nearly all modern CPUs into three distinct levels: L1, L2, and L3 cache.
Okay, let's detail that structure because understanding these internal layers tells you everything about the engineering priorities here. L1 is the smallest and fastest level, so what are the technical details on why it's so prized?
L1 is essentially the CPU's immediate muscle memory. It's typically split into two parts: the L1 instruction cache for the code and the L1 data cache for the values the code is using. And because L1 uses FRAM, that's static RAM, which is fast but complex and expensive, it is incredibly tiny. We're talking kilobytes per core,
Yes, kilobyte.
tens or hundreds of kilobytes. But crucially, access to L1 is instantaneous. It often takes only 1 to 4 CPU clock cycles. Think of L1 as the handful of ingredients the chef is actively holding in their hand: the salt, the pepper, the garlic they're chopping right now.
Okay, so why not just make L1 bigger? If it's so fast and so essential for keeping the chef working, why live with a limit of, say, 128 kilobytes? That seems really restrictive.
That's a fantastic question, and it hits right at those economic and physical constraints we talked about. If we made L1 cache larger, it would have two really detrimental effects. First, it would dramatically increase the physical size and heat output of the CPU die, which would raise manufacturing costs exponentially.
Of course.
But second, and this is more important, the physical distance the signal has to travel to query. That larger cache would increase the latency. Even at the speed of light, a greater distance requires more clock cycles. So making L1 significantly larger would inherently make it slower, which defeats its entire purpose.
So the size is an absolute optimization point for minimum latency. Okay, moving slightly outwards then, we hit L2 cache. Bigger than L1, but a bit slower.
Right. L2's is the prep counter, the small staging area. It holds data that is highly likely to be needed soon. Maybe data that was just kicked out of L1 or data that follows a predictable pattern. It provides a massive performance buffer. If the CPU misses an L1, which took, say, 1 to 4 cycles accessing L2, might take around 10 to 20 clock cycles. So still very fast. Oh, incredibly fast, exponentially faster going any further down the hierarchy. L2 tends to be measured in hundreds of kilobytes up to several megabytes per core. It's a necessary compromise.
And then the largest of the three on-die cache layers, L3 cache, which is shared across all the processor cores.
L3 is the general pantry for all the chefs, all the cores working in that single CPU kitchen. And since it's shared, it's the biggest of the three cache levels, sometimes tens of megabytes. But it's also the slowest of the three in terms of access, maybe 30 to 60 cycles. Its role is essential for keeping everything coherent across all the different working cores and acting as that final huge buffer before the processor has to go off chip entirely.
So this tiered approach, L1 being smallest and fastest, L3 being largest and slowest, it's the perfect micro-level illustration of that core trade-off we began with.
It is, exactly.
And now we can truly grasp why all this matters for our overall computer speed. When we say a modern CPU can perform billions of operations per second, that performance is only theoretical unless the data is right there.
The time cost is everything.
Mm.
If the data the CPU needs is in L1, the CPU gets a cache hit, gets the data in a few cycles, and can continue flying. If it misses L1 but finds it in L2, that's still excellent. But if it misses all three cache levels, what we call a cache miss, the CPU essentially has to halt operations. It enters a stall state. It waits.
The race car is stuck at the red light, and the moment we get a cache miss, we are now subjecting the CPU to data access delays that are orders of magnitude slower than what it's capable of.
Precisely. When the CPU has to look for data off chip, in the next layer down, which is RAM, the access time jumps from tens of clock cycles to potentially hundreds of cycles. That delay of maybe 50 to 100 nanoseconds in CPU terms, that's a massive amount of wasted potential. The CPU has to perform what's called a context switch, or just a wait cycle. This waiting, this stall, is the primary source of the microstutter people experience.
And the entire point of this elaborate cache structure is to leverage a scientific principle called locality of reference.
Ah, yes, locality of reference. That is the prediction engine that keeps the chef cooking. It operates on two principles: temporal locality and spatial locality. Temporal locality states that if a piece of data is used now, it is highly likely to be used again soon. So we keep it in the fastest cache layers.
And spatial locality covers the immediate neighborhood, so things that are close by.
Exactly. Spatial locality states that if the CPU accesses a specific piece of data, it is highly likely to need the data physically adjacent to it next. Think of processing an array, or just running code instructions one after another. We don't just load the single instruction the CPU needs. We load an entire block of data around it into the cache, anticipating the future need.
So the whole system is built around the idea that computing isn't random. If a program is working, it tends to focus its activity in a small, concentrated area of memory for a short period of time. As long as the data stays local, the computer flies. If it isn't local, the processor is grounded.
That's the perfect summary. Cache is crucial because it ensures the system exploits that predictability. If you maintain a high cache hit rate, meaning the data the CPU needs is usually found in L1, L2, or L3, you have a fast computer. If the workload constantly forces cache misses, the CPU spends most of its time idle, waiting for ingredients to be delivered from the next layer down, which is RAM.
Okay, moving down the hierarchy. We transition from that hyper-focused, tiny, ultra-fast cache to the next layer. Layer 2, the active workbench. This is where we find RAM, or random access memory.
Right. If cache is the chef's small, immediate countertop, RAM is the sprawling kitchen workspace. It is vastly larger than cache, typically measured in gigabytes, but it is fundamentally much slower. It sits off chip and is accessed via the memory bus.
This is the memory people are most familiar with when they talk about specs, the 16 gig or 32 gig number. And its role is to hold the data for everything you are actively doing right now.
That's right. When you boot your computer, load the operating system, open 20 browser tabs, launch a video editor. The system moves all the necessary files and data from the long-term storage up into RAM. RAM is volatile, of course, meaning if the power is cut, the data vanishes. But while the system is running, RAM keeps that massive pool of data ready and waiting for the CPU.
And this capacity is the smoothness factor we hear so much about, isn't it? Having enough RAM ensures effortlessness when you're switching between things. If I click from my game over to my browser, the data for both is just sitting safely in RAM, instantly accessible.
Exactly. RAM is medium speed. Accessing it takes longer than cache, but it's still fast enough that the slowdown is usually imperceptible. It allows for that effortless context switching that modern users demand. You want enough RAM to hold the active working set of all the programs you currently have open. But here's where it gets really interesting. We have to analyze the major catastrophic performance pitfall that occurs when RAM is insufficient.
This is the critical juncture. This is where the hierarchy breaks down and the computer speed just dissolves into a painful, real-world grind.
It is. When RAM runs out, meaning you're trying to load more active data than the physical memory chips can hold, the operating system has to get desperate. The virtual memory manager decides which least recently used pieces of data in RAM are expendable, and it moves them out. It moves them to the next layer down, the persistent storage drive, your SSD or your hard drive.
So the system starts using the slowest form of storage as a substitution for fast memory.
And there's a specific technical term for that desperate process. It's called swapping or paging. The operating system creates a large hidden file on the disk, the page file, and it uses this to shuffle data back and forth as if it were RAM.
That sounds like a technical necessity, but a performance disaster. You're literally telling the fastest part of your system, the CPU, that its ingredients are now in the basement freezer, not on the counter.
And the performance penalty is devastating. Remember the speed gaps. Accessing data in RAM might take 50 to 100 nanoseconds. Accessing data that has been swapped out on even a fast SSD could take hundreds of microseconds. Milliseconds on an old hard drive. That is a thousands-fold penalty just for running out of space on one chip.
You've shifted the latency from nanoseconds to potentially milliseconds. This is the moment when everything can suddenly feel sluggish.
Precisely. We can break down the consequences. When the CPU requests a page of data and the system realizes it's been swapped out, that's called a page fault. If the system only has to retrieve that page from the swap file, it causes a noticeable slowdown, a soft fault. But if the system has to simultaneously retrieve the requested page and make room for it by writing another page back out to the disk, that is when the entire machine freezes momentarily. That's a hard fault.
And if this cycle starts repeating constantly, where the system is spending all its time swapping data in and out of the storage drive just to keep things running, that's called thrashing, right?
Thrashing is the ultimate sign of RAM insufficiency. It's the sound of the system fighting against the hierarchy itself. It's trying to defy physics by treating slow storage like fast memory, and the result is an utterly ruined user experience. The reason your computer can suddenly seize up for 5 seconds is that the system is trying to write out a gigabyte of data to the swap file, and until that's done, the CPU can't proceed.
So when your computer feels like it's struggling to switch between two demanding apps, or launching a new browser tab makes everything stall, That is a classic case of the system actively swapping. You've hit the layer 2 wall, and the whole workflow is now subject to the speed of your slowest component.
And this is why the question, how much RAM do I need, is so critical.
Uh,
The answer isn't a fixed number. It's always enough to prevent paging. Because once you start paging, you've effectively negated the benefits of your expensive, fast CPU and cache. The chef is perpetually walking to the basement.
okay, let's talk about that basement layer 3, the final and slowest layer in the primary hierarchy. We've established the cache is the countertop, RAM is the workbench, layer 3 is the library persistent storage.
This is the bottom layer, the massive final repository. This includes your solid-state drives, SSDs, or traditional hard disk drives, HDDs.
And the defining non-negotiable characteristic here is persistence.
Absolutely essential. This is the permanent home for data. When you shut down the power, this is the only layer that retains the operating system, your apps, your photos. It's the collective long-term memory of the computer, built for capacity and affordability, not for speed.
Now, in the last decade, we've seen a massive shift from those old mechanical spinning hard disk drives into the flash memory of solid-state drives. And everyone agrees SSDs are faster, but we need to put that speed into context using the hierarchy as our measuring stick.
We must. We have to highlight the stark difference in speeds. While SSDs have been revolutionary, I mean truly revolutionary, the fundamental rule of the hierarchy holds firm, they are still orders of magnitude slower than RAM.
Can you give us the scale comparison in terms of latency? Because that's what really matters to the CPU.
The scale difference is just immense. If an operation in L1 cache takes, say, 1 to 4 clock cycles, and accessing RAM takes 50 to 100 cycles, accessing persistent data involves a massive jump. Retrieving a block of data from a modern, fast NVMe SSD might take 20,000 to 100,000 clock cycles, and retrieving the same block from an old spinning HDD, that could easily take millions of clock cycles. You're waiting for physical parts to move.
So the jump from cache to RAM is a large speed drop, but the jump from RAM to persistent storage is not a cliff, it's a canyon. It's a completely different scale of delay.
It is a canyon defined by the physics of data storage. RAM uses electrical signals. Storage relies on complex controllers, reading flash cells, or the physical movement of mechanical arms. And this fundamental disparity explains the user experience of load time.
Okay, let's break down that load time. Why does launching a big application or opening a massive project file take 15 seconds, even on a fast computer?
Because that entire process is the movement of immense amounts of data, hundreds of megabytes, maybe gigabytes, from the slow, persistent storage layer, layer 3, up into the medium-speed RAM, layer 2. The CPU is almost entirely idle during this period. It's just waiting.
It's the time taken to move the entire recipe book from the library up to the active workbench.
Exactly. And only after that massive data transfer is complete and the recipe book is sitting in RAM, does the chef, the CPU, start pulling small, relevant chunks of it up into the cache to actually work with it. The entire load time bottleneck is layer 3's transfer rate. It's the speed of your storage device. This is the difference between a system booting in 5 seconds on an NVMe SSD versus taking 3 agonizing minutes on an old HDD.
So if I have a super fast CPU and a huge amount of RAM, but I'm still using an older, slower storage solution, my boot time and my application launch times will be fundamentally throttled. The most capable parts of my system are just wasted.
Completely wasted. The initial data movement is entirely bottlenecked by the speed of the disk. Until that data is safely in RAM, the fastest parts of the hierarchy are just idle. This is why upgrading a computer from an HDD to even a basic SSD often results in the single biggest, most noticeable performance jump you can make. You are dramatically speeding up the lowest point of the primary hierarchy.
Okay, let's shift to synthesis now, connecting all these layers back to the feeling of speed. Back to that initial paradox. Now we can definitively say, waiting is the enemy.
The sources drive this core truth home. A modern CPU is capable of billions of operations per second, but that capability is fragile. It's the hierarchy that dictates the real-world speed. We're dealing with a system that can execute instructions at light speed, but is physically constrained by the sluggish speed of data transportation.
The moment the CPU has to wait, the system's performance just collapses into whatever the access speed of the next lower layer is. It's a beautifully efficient system when data is where it needs to be, but it becomes cripplingly inefficient the moment the data is too far away.
Right. If the CPU is forced to wait for data from RAM, or worse, from storage, it's stuck at that metaphorical red light. Think about what that means for highly optimized code, like a database query. A programmer might write an incredibly efficient algorithm, but if that algorithm relies on reading a massive data set that exceeds the size of RAM, well, the performance is entirely defined by the data access delay, not the calculation itself. The CPU is functionally idle, while the slow I/O input operations complete.
Therefore, we can conclude that many real-world slowdowns, the kind that frustrate users the most, stem entirely from these memory access delays, not from weak processors. The processor is almost never the bottleneck, it's just starving.
hmm And this leads us directly to analyzing the practical implication, why the same computer performs so differently depending on the task. If we connect this to the bigger picture, we can understand two distinct daily performance experiences our listener has.
The first experience being the light, instant feeling, the computer behaving exactly as it should.
This happens with tasks that have high locality of reference and fit well within the cache and RAM envelope. Think about light browsing, editing a small document, chatting. The working set of data is small. It lives entirely in RAM, and the most active parts are instantly pulled into cache. The CPU is rarely stalled. The speed feels instant. You feel the full power.
And the second experience is that heavy feeling, the stuttering, the sluggishness.
This occurs when the working set of data is massive, forcing constant movement across the hierarchy, especially involving layer 3. Examples would be loading huge datasets, rendering a complex 4K video project, or playing a large open-world game that streams textures. Because these tasks require continuous massive reading and writing of data between slow storage and active RAM, the system spends all its time managing slow data transfer rates, and the entire computer just feels heavy.
The analogy holds perfectly. The same chef, same kitchen. But one task uses only the ingredients on the counter, and the other requires continuous trips to the warehouse across town. It explains everything about the variable performance we experience daily.
And it highlights that performance is a function of the task's data requirements versus the available memory resources, not just the raw clock speed. The bottleneck shifts depending on whether you are stressing layer 1 and 2 capacity or layer 3 transfer rate.
We've established the theoretical framework, diving deep into the L1 structure, the RAM pitfalls, the storage reality check. Now, we transition from theory to practical diagnosis, the ultimate payoff for you, the learner. We need to translate this hierarchy into actionable knowledge.
Exactly. The point of understanding the 3 layers isn't just academic. It means that when you perceive a slowdown, you can pinpoint the bottleneck based on the symptoms. You don't have to guess.
So what does this all mean? It means when your computer feels slow, you don't need to guess if you need a better CPU. You can determine which part of the hierarchy is stressed. We can simplify this into a diagnostic checklist of 3 clear questions.
Question 1. RAM limitation. The first question to ask yourself when performance drops off dramatically, particularly during multitasking, is, am I running out of RAM? Or, technically, am I forcing my system to page excessively?
This focuses entirely on layer 2 and the catastrophic effect of swapping. The symptoms are unmistakable. The computer slows down dramatically when you switch between applications or when you have too many browser tabs open. That immediate loss of responsiveness across the board is a classic signature of the system fighting to shuffle data between RAM and the swap file.
Let's use a concrete example. Say you're a financial analyst running a complex model in Excel, you launch a virtual machine, and you're indexing a massive database. And the system suddenly starts taking seconds to draw a new window. That isn't a CPU problem. That means your combined active dataset is too big for your physical RAM. The system is thrashing. Your working set needs 24 gigs, but you only have 16.
And the solution isn't a new processor, it's simply more physical RAM, or maybe just changing your workflow, closing things you don't need.
Exactly. Question 2, storage limitation. The next question addresses layer 3. Is my task fundamentally limited by the storage transfer rate?
This is a bottleneck where the symptoms are very specific. Slow boot times, slow application launch times, long save, and load times for very large files. The user experience is one of a long, predictable wait, followed by perfectly normal operation once the task is loaded.
Consider a professional photographer. If they open a massive 15-gigabyte raw photo catalog and the initial loading screen takes 5 minutes, that is a layer 3 limitation. The speed is limited by the rate at which the computer can physically move 15 GB of data from the SSD up to RAM. Once those assets are in RAM, scrolling might be instant, but the initial transfer time is all layer 3.
And this diagnosis tells you precisely what upgrade is needed: a faster drive. Moving from an older SSD to a modern NVMe drive, the CPU speed is irrelevant to that specific delay.
Finally, question 3, workflow limitation. Is my workflow constantly moving huge data around, creating continuous data requests that overwhelm the memory bus? This focuses on the continuous back and forth movement between layer 3 and layer 2.
This is the nuanced, sustained problem faced by professionals dealing with massive datasets under continuous pressure. It's not just the initial load time, it's the continuous taxing strain on the entire hierarchy.
A great example is texture streaming in modern open-world games. As a player flies quickly across the map, the system has to continuously load new textures from the SSD into RAM. If the storage drive can only deliver 500 megabytes per second, but the game is requesting 800 megabytes per second to keep things sharp, the game will stutter. You'll see blurry, low-res assets until the Layer 3 transfer catches up. It's a sustained I/O bottleneck.
In those sustained high-demand scenarios, the solution requires a more comprehensive approach. You need massive amounts of RAM to try and hold the entire working data set in memory, and you need the fastest possible storage to minimize the delay when those trips are unavoidable.
And this comprehensive diagnostic checklist is the core takeaway. By internalizing the memory hierarchy, the chef, the workbench, the library, you can move past the frustrating guesswork. The slowdowns are predictable, logical consequences of how data is waiting to reach the chef.
So when you feel that stutter, you now know how to look for the failure point. Is the chef out of space on the counter? Is the workbench overloaded? Or is the initial delivery from the library just taking too long?
Understanding the memory hierarchy allows you to diagnose performance without guessing. It empowers you to make informed decisions about whether the next necessary upgrade is more RAM, a faster drive, or maybe finally, a CPU with a larger cache.
This deep dive has been incredibly illuminating. We've gone from the tiniest, fastest nanoseconds of L1 cache all the way down to the massive terabytes on the SSD. And we've definitively shown that speed is fundamentally about how quickly data reaches the processor. It's not about raw horsepower, it's about efficient logistics.
It's a real testament to engineering brilliance, designing a tiered system that compensates for the physical limitations of material science and economics. They built a magnificent data transport system around an impossible trade-off.
Which sets us up perfectly for our next exploration. The sources hinted at a necessary follow-up, zooming in on that critical boundary between Layer 2 and Layer 3. We kept mentioning the revolutionary shift to SSDs. Next time, we'll dive deeper into storage to answer the common question. SSD versus HDD, what's the real difference, and why did that shift change everything?
Fascinating stuff indeed. But before we wrap up, I want to leave our listener with a final provocative thought, building on that fundamental three-pronged trade-off we established at the very beginning.
Lay it on us, the speed, size, and cheapness triangle.
We established that the entire memory hierarchy exists because we cannot have all three: speed, size, and cheapness. This constraint has governed computer architecture for decades. This raises an important question.
What would happen if that foundational constraint were suddenly just obliterated by a genuine breakthrough?
Exactly. What would happen to computing and architecture if a new theoretical storage technology suddenly made one of those three variables dramatically less expensive without sacrificing the other two? Imagine a new type of non-volatile memory that was as fast as L1 cache, few nanoseconds access time, but could be manufactured for the price of standard DRAM and scale up to petabytes.
That would entirely redefine the concept of a computer. It would make nearly everything we discussed today obsolete. You wouldn't need the complexity of L1, L2, L3, and separate physical RAM and storage. The whole waiting problem would just disappear.
The hierarchy would collapse into a single, massive, instantaneous pool of memory. The current necessity for continuous data shuffling, paging, swapping, lengthy load times would become historical artifacts. The computer architecture would become radically simpler because the processor could simply request any piece of data and know it would arrive instantly. That fundamental, persistent trade-off is why we study the hierarchy today, because breaking it would truly unleash a new, unimagined era of computational design.
A wonderful, thought-provoking scenario to consider. Thank you for guiding us through this essential deep dive into the logistics of data. We'll catch you next time as we keep digging into the details that make the digital world run.